Hello, my dears. This is the start of our last unit of chemistry, which is energy. I know you guys are all very upset that this is our last unit, but congratulations, you made it. It's going to talk a lot about thermodynamics, something called enthalpy, which I'm going to get to in a moment, and determining how much energy is lost or gained in a reaction. So we're going to go ahead and get started. This is the first page of your energy notes packet. And you will have to copy this down along with your notes. So I'm just going to go over the basic definitions of, things I'm going to be referring to a lot. I'm going to say enthalpy a lot. I'm going to say the system a lot in these upcoming videos. So it is important that you know what I'm referring to when I mention those things. The first law of thermodynamics is kind of this overarching principle that goes through all of chemistry. It might remind you of the law of conservation of matter. But the first law says that energy can never be created or destroyed. Okay, so the total energy of the universe is constant. So we can observe energy changes in the world around us, but we can never actually create or destroy energy. Rather, energy is transferred from one part of the universe to another. Okay, so rather it is transformed, not so much created. Okay, the system is what we are observing. The surroundings is everything that is not part of the system. So, for example, if you're talking about a cup of ice water, the cup of ice water is the system, and then the surroundings is the room or the countertop that it sits on. So basically everything around the system. Okay. Kinetic energy, you guys know this very well. It's energy of motion, so energy of movement. Thermal energy is the energy of heat. So, as particles move very quickly, they have higher thermal energy. Potential energy is stored energy. So, this is the classic, you're holding up a ball on top of, the staircase. That ball that you're holding as you're about to let it fall, that ball has potential energy. So it's stored energy. Chemical energy is the energy stored in chemical bonds. We talked about this in our chemical reactions unit. We said that a triple bond is very strong and a single bond is the weakest of the bonds. And then enthalpy, you may have heard of enthalpy before, maybe in 8th grade science. But enthalpy is the amount of energy absorbed or released during a chemical reaction. Sometimes we just call it heat, or also other times we just call it energy. But the fancy term for it is enthalpy. Okay? And then when we talk about the system and the surroundings, there's two words that you have to understand, and that's endothermic and exothermic. Endothermic is when the energy from the surroundings enters the system, so therefore heat is absorbed, okay, and that's noted by a positive value for enthalpy. Again, enthalpy is noted as H. Okay, so when heat is absorbed, that is going to feel colder to the touch. An exothermic reaction is when energy is going from the system to the surroundings. Therefore, the heat is released, and that is going to feel a lot warmer. Okay, and we're going to note that with a negative value for enthalpy. Okay, so this is on the bottom of your first page of notes, and there are some symbols that as you go deeper into science, you're going to have to know, especially when you get into physics as well. So this little triangle symbol is the Greek letter delta, and delta represents a change in enthalpy. So for example, when you want to determine the change in enthalpy for a reaction, it's the heat of the products minus the heat of the reactants, which makes sense because if you want to determine the total energy of the system, you can subtract the energy of the products that were made minus how much energy you put into the system, and that gives you the overall energy that was put in or used. Okay, so when you subtract the energy of the products minus the energy of the reactants and you get a positive value, that indicates that heat was absorbed. Okay, so if heat is positive or if it was absorbed, that means that it is an endothermic reaction. So keep in mind that endo is Greek for into, and exo is Greek for out of or exiting from. Okay, so if heat is absorbed, heat is going into the system, then it is endothermic. Okay, if you subtract the products minus the reactants and you get a negative value, that means that heat was released and the reactants have greater energy than the products. So if heat was released, then this is an exothermic reaction. Okay. You also see this little degree symbol. This signifies the reaction is the standard enthalpy change. And then you'll also see RXN. That just means reaction. That's shorthand. Most of you in my class should know that, but I always abbreviated reactions as RXN. So that should hopefully not be new to you. And if the little degree symbol is confusing you, just keep in mind that a standard state is the state of matter that pure substance exists in. Okay, so it could be a solid, a liquid, or a gas. Okay, so on the next page of your notes, you have these little practice of determining whether the enthalpies are exothermic or endothermic. What you need to look out for is if delta H, the change in enthalpy, is a negative value or a positive value. If it's negative, that means that heat was released and it is an exothermic reaction. If the enthalpy is positive, then that means heat was absorbed into the reaction and that is endothermic. Okay, so for example, the first one we have negative 393.5, it's negative exothermic, positive endothermic. Okay? Okay, so moving forward on page 2 of your notes, there's something that is noted that you need to be familiar with, and it's called a thermochemical equation. And a thermochemical equation takes into account what's happening in the reaction, and then it also includes the enthalpy for that overall reaction. Okay, so for example, in this one, this is the synthesis of sulfite. So we have sulfur and oxygen forming SO2, and they tell you that the enthalpy is negative 296 kilojoules. So that tells us that this equation is exothermic, okay? And then over here, this is the opposite of the reaction. So here we were synthesizing. So this is a synthesis reaction because we have one product. But here this is decomposition because we have one reactant, okay? So if you notice, this is the same number, only it's the opposite. Okay, now what we're really trying to show you here is that these are essentially the same reaction. Okay, so a molar heat ratio is a ratio that is made from the coefficients of a balanced equation and the enthalpy of that reaction. Okay, so now we're going a little bit more advanced. We're not only taking into account the energy that's put into the system, but we are looking at the stoichiometric ratio of what's happening there. Okay, so an example for you is nitrogen plus oxygen gas forming nitrite. So the first thing we have to do is make sure that it's balanced. So we have 1 in front of the nitrogen, 2 in front of the oxygen, and we need a 2 in front of the NO2. Okay, So they're saying how much heat is produced, so we're looking for enthalpy, if we have 4 moles of oxygen. Okay, well, the reaction says that if you have 2 moles of oxygen, that's going to form 67.6 kilojoules of energy. Okay, so essentially what we're going to have to do is double this value. Okay, so if I have, for every 2, hold on. So I started with a clean slate here just to kind of help you guys see. The previous slide just kind of had an overview of everything I was saying, but now I'm going to go in and kind of help you guys see it from the way that we've always done it, which is the guess method. Okay, so you still have your balanced chemical equation. You know how much energy went into that reaction. So now we're going to determine how much heat was made with 4 moles of oxygen. Okay, so we have our given is 4 moles. Okay, and then the equation says that for every 2 moles of oxygen, that produces 68 kilojoules of energy. Okay, so essentially you're going to double this value. So 4 times 68 divided by 2 will give you your answer. Okay, it's the same thing with when it says, what about 4 moles of nitrogen? Okay, well, I have 4 moles of nitrogen. Per the equation, only 1, this is a 1 here, 1 mole of nitrogen makes 68 kilojoules of energy. Okay, so I know you guys aren't used to seeing kilojoules over moles, but kilojoules per mole is actually how we measure enthalpy. So it makes sense. So these are going to cancel out, and you're going to get left with kilojoules, which is what you're looking for. Okay, so this one is... So when we do our calculations, we get 135.2 kilojoules when we doubled our oxygen, and then 270.4 kilojoules when we quadrupled our nitrogen. Okay, so this is basically the same way that you've always been doing it, starting with your given, using that equivalent unit diagonally per the diagonal rule, and our desired unit is energy because it said how much heat is produced. Okay, and we are going to continue the same exact method with our next video, which is thermochemical stoichiometry. So I will see you next time.